Okay, so today I'm going to be talking about geophysical inverse problems. That's a pretty pompous title for my lecture because there's no way I can cover anything in any detail in 1 hour. So I'm actually going to really focus on seismic tomography. And my talk is going to be in 2 parts. One, some general introduction to the basics of inverse theory based on an example of seismic travel type tomography. And then the second part of the talk will be more of a discussion of the attributes of seismic tomographic models, very specifically from the point of view of global tomography, which, okay, so seismic travel time tomography, the ideal case here, idealized case, which applies to any kind of tomography, either seismic or medical or any kind of topic of the same kind, where you send some waves through a body and you want to find out the structure of the body. So in this case, you see we have a background model in blue. It's here called FAST, but let's call it the background model. And we have a slow anomaly, and we have some sources here on these 2 sides and receivers on this side, which are measuring seismic waves or acoustic waves, or whatever, and travel times of these waves. And you can see that if you have a dense enough network on both sides, if you look first at those horizontal ones, if your travel path goes through the anomaly, the arrival of the wave will be late compared to what it is in the background model. And so with this distribution of receivers, you can tell that you have some anomaly in this region. However, you cannot localize it very precisely because you only have ray paths in this direction. So for a given travel time anomaly, you could distribute it all over this path, or you could concentrate it in one little area. You cannot tell. However, if you have also paths going in the other direction, then these paths also will show late arrival for those paths that travel through the anomaly. And you can see that if you have both these and these, you can locate the anomaly between here and here, and between here and here. So then it's a matter of how you parameterize your model, whether you're going to be able to resolve its geometry in great detail or not, and also how many of these paths you actually have. And once you can see, however, that if you have a very good geometry, you can determine the geometry of the anomaly and also its strength, because once you have your geometry and say some assumptions on the fact that it's uniform, you can get the strength of this anomaly. Okay. In practice, of course, in seismic tomography, rays in the Earth, rays are curved, as Ed showed us in his lecture. And so the geometry is somewhat different, but the principle is the same. You have a background model which tells you, to first order how the ray paths are going to be, and then you set up a tomographic inversion in that model. So the principle kind of is this. Now let's turn this into equation. So in the background reference model, the travel time t along a particular ray gamma is the integral over the ray of the travel time along an infinitesimal length ds, which is ds divided by the velocity in the model. Okay, so this is in the background model. I call it v0. Okay, and preferably we express this in terms of the slowness, which is the inverse of the velocity, which makes the relationship given a travel path linear in the velocity, in the slowness. The ray path itself is determined by the velocity structure using Snell's law, which Ed discussed. And this is already, you see that here we have made some assumptions, some theoretical assumptions. We have assumed that the structure is such that you can assume that the ray path obeys Snell's law, and it basically goes through the shortest path given a velocity structure between the source and the receiver, and that the travel time depends only on the velocity along this infinitesimal path. This is infinite frequency approximation ray theory. Now suppose the slowness is perturbed by a small amount. The small amount that's small enough that the ray path is not changed. Then the travel time is changed by delta t equals integral over the ray of the delta uds, which is delta v over v0 squared with a minus sign. And so you have the expression of the travel time with respect to your velocity perturbation, which is what you want to determine. Okay. So again, that equation is over there. We need to do one more step in order to solve this problem in practice. You have to somehow parameterize. So a typical way of parameterizing is using blocks, but you have many other ways of parameterizing. You can choose a basis function to describe your space. But let's just look at what happens if you have blocks. So you parameterize your model in some blocks, and you can see that here again you have to make a decision that what is going to be your parameterization. You already made the decision that you believed in ray theory. Now you're making the decision that you can parameterize in certain blocks. You're going to have to choose the size of the blocks that would be appropriate for your model, for your modeling. Or for your particular geometry and data set. But we can assume that the velocity perturbation in each block is constant in the block. So that will be a delta v j in block j. And we like to express it in relative perturbations to the reference model. So it will be delta v over v0 here. And so you can see that if you discretize, so you replace this integral by a sum over the blocks, you get a sum over the number of blocks, j equals 1 to m, of the perturbation in each block times something that you know because you've already assumed your theory and you've already assumed your parameterization. And in this particular case, this gij is the length of the path in each block divided by the velocity in the reference model. So it's something that is known, right? It's your kernel in a way. So, Question? Question? Yes. No. Okay. So ray theory is a pretty good first approximation for travel times of short period waves. But if you want to study, seismogram that has many frequencies in it, etc., you have to worry about the relation of your frequency with respect to the actual wavelength of your model, right? You have to have a smooth model for ray theory to be valid. Yes?
In the last slide, you made the assumption that a small perturbation of the velocity structure doesn't change the ray.
Yes.
But how strong was that? I mean, how much of the perturbation kind of law?
Well, that's. I mean, typically you would, a few percent. But yeah, okay. Well, I'll discuss this in more detail a little bit more. So solving the problem given a set of travel time perturbation delta ti, right? So the travel time perturbation is expressed with respect to this reference model. Here, a velocity model that depends, say, on depth. If you're a model such as PREM, which is a 1D reference model of the Earth, if we're studying in the global scale. So you express this travel time as with respect to the expected travel time in your reference model on an ensemble of rays. These are your data. Determine the perturbations dV in each block in a 3D model parameterized in these blocks is solving an inverse problem, which is of yes.
So you use spatial parameterization in terms of blocks.
Yes.
Can you parameterize your model in terms of, for example, scalars, sphere harmonics?
Yes, you can parameterize your model in any type of basis function, anything that can describe the space, preferably in a unique manner. I mean, that is, your functions, separate, right? They're independent. So you can see that this equation here is of the form delta D. I write it in delta, where this is your data, and I write it in delta D too. So you remember this is with respect to a reference model. So this is your model vector. This is all the travel time perturbations at all of your stations that you have, right, put into a vector of size n, where n is the number of data that you have, the number of stations, equals this matrix G, of whose elements are this, times your delta m, which is your perturbation to the model, which is essentially the difference between your model in your 3D model that you're trying to determine and the reference model, say the 1D model. So you can write this like this, or you can, of course, express it explicitly in this term. So you have n equations and m unknowns. Again, this G has the dimensions m times n. Usually, you try to have a situation where you have a number of rays larger than a number of blocks, which is then called an overdetermined system. Sometimes you have problems where you have more unknowns than data, which is called an underdetermined system. Generally, the problems that we study are mixed, that is both overdetermined and underdetermined, but I won't go into this in too much detail. So how do you solve this problem? N is not equal to m, so this matrix is not square. So you have to find a way to find delta m from this problem, to invert this, right? To find delta m as a function of delta d, but you don't have a square matrix. So a standard way to do it, if all conditions are right, is to simply multiply by the transpose of this matrix, gt, both sides of this equation, and you get this equation. Now this matrix is a square matrix with dimensions m by m, the number of model parameters. So we know how to invert a square matrix if it is invertible, that is, if its null space is not 0. So if that matrix has an inverse, we can write the solution as gm equals the inverse of this matrix times gtd, right? You multiply on both sides by gtg minus 1. And the inverse is in the sense that the product of this matrix, this inverse matrix by the matrix, is equal to the identity matrix, so the matrix which has ones on the diagonal. And this is called the least squares solution, and you find the solution by solving the problem of minimizing the distance between your data and your predictions, the model times the matrix G. Here, in a very specific sense, in the sense of the L2 norm, which is the standard distance that we use in geometry, which is if you have a vector, you take all its elements, take the norm of each element to the square and sum, right? So that's the distance. So distances and norms, actually this is a norm, can be chosen in different ways, but this is the most standard one. Okay, so the least square solution minimizes this distance between the data and the predictions, which is something nice, which is something that we want. Note that I already said the G contains assumptions and choices, the theory of wave propagation, here the ray theory, and parameterization, blocks of some size, or other basis functions. Now, in practice, things are more complicated because in general, this matrix GTG is not invertible, it's singular. So if you say, think in terms of eigenvalues, it will have some null eigenvalues, right? And there will be a null space. So in fact, there will be an infinite number of solutions. You can add to any solution a solution in the null space, and that's a solution. Okay, so you have a problem. And why is this matrix singular? Because if you have ray paths, some blocks may never be reached. So if block is not reached, the length of paths in that block for that ray is going to be 0, right? And so you're going to have 0 elements in this matrix, and when you square it, you're going to have a problem. You basically can't resolve anything in these blocks. So you can put any structure, and that's going to be fine for this. So how do we choose a solution? In order to choose a solution, we have to add some constraints. We have to add some independent information or some constraints. We can choose a standard way of doing is find a special solution that can maximize or minimize some desirable property through a description, through a norm, a distance to something. So for example, find the model with the smallest size, right? The smallest size here, which we can write, would be the square of the model parameters, square root of this, which I can write also as vector m multiplied by vector m transpose. Actually, that would be the square, sorry, of this. Or you can choose the closest possible solution to a preconceived model. So you will want to minimize the norm of m minus this preconceived model m. And this process is called generally regularization. Yes?
Do you have to do regularization in a finite frequency model?
Yes, also. I'll show you why. Because what's very important, I mean, if we talk in the context of travel time tomography, what's really dominant in that case, especially on the global scale, is actually the sampling, right? Even if you have finite frequency, you are still kind of bothered. Well, the sampling is not adequate. I'll show you some of this. Something we do quite frequently, the way we pose this problem is to minimize some combination of the misfit, right, the distance between the data and the predictions from your model, and the solution size. And the way to cast it is you have this functional, which depends on the model, which is this is the distance from, this is the misfit here, squared, plus some weight parameter times the norm, right, of the model. And you minimize this functional, and if you work it out, compute the partial derivatives with respect to each model parameter, you find this solution, which is called the damped least square solution, which is like the least square solution, but now you've added this parameter epsilon squared to the diagonal. So you've modified your matrix in a way that will make it invertible. If epsilon is large enough, this will be, and this general, this can be referred to also as Tikhonov regularization. And so you see that you here have a parameter that you can play with. It's something that is not necessarily determined very rigorously. Yes? No, I mean the size of the velocity perturbation in each block. Yes. That's what I mean. Yeah, of course you can. I mean, this is with respect to a given parameterization, right? So you've set your parameterization, you've set the size of your blocks, and once you've set the size of the blocks, you want to minimize the size of your model inside the block. That's one way of doing it. It's called norm damping. But of course, you may want to go back and see whether you chose the size of your block properly or not. And if you don't have enough data, enough constraints, then increasing the size of your block will make sure that rays that didn't pass in, that blocks that were not sampled by rays will be eventually sampled by rays, right? If you really increase your blocks. That's the goal, is to find the model, right? To find the perturbation. But because you don't have enough constraints, you have to make some assumptions. You have to add some. Okay, so in this problem, we can minimize the model size, as we were just discussing. The model size meaning the size of the perturbation in each blocks. And that's called norm damping. But we could choose to minimize something else. For example, we could choose to minimize the difference between the model values between two adjacent blocks, for example. So we want to smooth the model, right? So this can be expressed mathematically by this matrix here, this matrix, which here you can see the product of M by the matrix D will be the difference between, the first line is the difference between model parameter 1 and model parameter 2. This is one will be model parameter 2 or model parameter 3 minus model parameter 2, etc. Right? So if you arrange your model vector so as to have the, count the blocks so that they are counted, adjacent to each other, then this will lead to a smoothing. It's like a smoothing operator. And so instead of minimizing this thing, you will minimize this dm times dm transposed, which can be written as m transpose d transpose dm, or m transpose times a weighting matrix m times m. Okay, so you introduce something in here that can be the diagonal matrix if you're norm damping, can be your first derivatives, or it could be second derivatives, roughness, etc. More generally, you can minimize this quantity, which then has this weighting matrix that you have defined, like here, for example. And on both sides, you have also a reference model, right? Model that you want to be close to or stay close to. And more generally, I'm not going to get into the details, but you can write the solution. You can also include weights in your both on the model parameters and the data, and you get an expression like this. Let's not worry about it too much. If you are really interested, you should read the paper by Tarantella and Valette, 1982, or the book by Tarantella, 1985, of inverse problem theory, which includes a very detailed and rigorous discussion of nonlinear problems, because most of the problems we're looking at are initially nonlinear, and in order to cast them in this format, you have to first linearize them. That's why we looked at perturbations with respect to a reference model, rather than directly trying to solve for the 3D model. And so you can imagine that in addition to the theory, which we made some assumptions on, in addition to the parameterization, we also have to make the assumption that our reference model is a good reference model, that we can be close to the reference model. So one concept I want to introduce quickly also. So there is no inverse to that initial matrix G, first of all, because it's not even square. Second of all, even if you but we've went through the process of how we can still get a model with all its imperfections from the data, and in the least squares case, this involves this matrix which we call the generalized inverse, which is of this form, so GT times the inverse of this GTG, right? If this is not well conditioned, if it has a null space, then we also discuss the damped least square solution, where you've added this parameter epsilon here, and this is a very simplified view of things, but for today's purpose, I will stop here. And in any case, you get this matrix, which is called the generalized inverse. If your model was a square, if you had a square matrix, and if it was well conditioned, G minus G would just be the inverse, the real inverse. But in general, in the problems we deal with in geophysics, it's not. So this parameter epsilon. So as you increase the damping, right, you have to choose it. So that's another thing we have to worry about. How do you choose this parameter epsilon? If you choose it to be very small, then you're favoring fitting the data. As you increase this, you will favor having a small norm of the model, right? Because you're trying to minimize the sum of the difference of the sum of the misfit plus epsilon squared times the norm of the model, right? So epsilon is a weight for these two quantities. And so basically you have this, you can choose various damping parameters, theta, and decide what is the level of a norm here given by eta that is acceptable, but and then choose your model somewhere along this line. But you can see that if you decrease the norm, then your misfit increases and can become very large. So this is actually something that's not rigorous. Typically, people will choose a solution here somewhere in the in the knee of this so-called L curve. But this is, you have to do a trade-off analysis and basically figure out independent ways of assessing what is a reasonable size of your model and what is a reasonable model given all of these these three parameters to play with. Okay. Yes.
You mentioned before that we can constrain the velocity contrast between adjacent grades to be continuous. Is that made separate from this regularization? I mean, because if you merge that kind of matrix to your inversion matrix, then your whole matrix cannot be singular, and then you don't really need to damp using this IGTG regularization.
I'm sorry, I don't. I mean,
the main reason that we apply this regularization is for some grade, if there are no rates to penetrate that, we need to give a constraint to that.
Well, no, it's not the only reason. It's because you already made some assumptions on the theory. You made an assumption on your parameterization, and I just gave you sort of an example that one of the problems you might have is that some rays don't sample. Some blocks are never sampled. But there, I mean, that's the main reason, right? But there are other reasons also for which your matrix is not well conditioned. That is the main reason. But so why would you? I mean, if you had a system where you had all the rays, all the blocks were sampled by many ray paths coming from many directions, and if you assume that ray theory is valid, then you would find a unique solution. You would not need to regularize. But this is never the case, unfortunately.
But I mean, in the finite fault inversion,
yes.
We don't. I don't really use this IGTG regulation because one way constrain the adjacent node to be continuous, and then even if there are some really low resolution node, it will be constrained by the slip of the adjacent node. So.
Well, yes. Okay. So it depends. But you already made an assumption on the smoothness of your model, right?
Yeah.
Okay. So that's an assumption which goes into. You have to have a parameter of how much the smoothness is important, right? So you could have this same kind of curves here, where it wouldn't be the model norm, but some other quantity that you're trying to. Yeah. Yes.
If you constrain the jump between two neighboring blocks, that is regularization.
Yes.
It is one choice.
Yes. Yes.
Another choice would be to just minimize each block, the value of each block. It's also regularization. You can do whatever you want, but they are all regularizations. And even if you constrain the jump between neighboring blocks, you also have a factor in front of it that you have to tune. If you set that really large, then you always get zero solution, right? Because the only solution that satisfies no jump is that. So that's also regularization. And you have the same curve.
Oh, yeah.
Yes.
However, can you get an additional constraint on the damping parameter by using satisfies from tomography?
Yes, I'm going to talk about this more, of course. But what you have to realize also that because you've introduced this fudge parameter, these damping parameters, whichever way you want to define them, you lose constraint on your actual model size. You can't recover the size of the velocity perturbation very precisely, right? Because it is dependent on your damping. So that's one issue that you have to be aware of. The other thing is you can't really do a rigorous assessment of errors, because your errors will have been kind of perturbed or modified by the introduction of these parameters. So there are many issues with this. One concept which is used a lot is the resolution matrix. Asking the question, how accurately is the value of an inversion parameter recovered? So how accurate is the velocity perturbation in a given block recovered? Or you can ask another question: is how small of an object can be imaged, right? So typically people will do this through the introduction of the so-called model resolution matrix. If you have your estimated model here, m hat, which is written here as introducing this generalized inverse, g to the minus g, times the vector of observations, you can plug in the original problem into this D, right? D equals G M true. Your original problem was solving what is the model that gives me the data, so D equals G M true. If you plug this in, you see that you get a relation between your true model, the model that you really want to know, and the model that you are obtaining through inversion, right? And so this is a matrix, which is a square matrix of whose number of parameters is m by m being the number of model parameters. And you get the relationship m estimated is R m true. So R is the resolution matrix, and it's like a space. It basically tells you what is the spatial filter that is applied to the true model to produce the estimated values. What does this imperfect inversion process do to your true model? Of course, you don't know the true model. So the way this is used is, in general, is that you plug in some synthetic model, like, for example, a spike. One block has a velocity perturbation of 1, say, or something, and all the rest of the model is 0. And then you see what the product of R M true gives you, and this gives you how that model parameter is actually maybe spread over several blocks, or its amplitude has been distorted by the process of inversion. So it tells you something about the imperfections of your inversion, or how good it is. So you can use a spike, right? Or you can use whatever your parameter, depending on your parameterization, or you can even choose, or you can use something that's more efficient. Efficient in general is the use of these checkerboards, right? So this is an example from I took these from slides that Guy Masters showed at the last CIDER. This is one global tomographic model. I'll be going into details of how this was constructed later. This type of model was constructed later, but it gives you sort of the model after inversion at different depths. And then you can go back and see how you constructed this model, what G matrix you used, what is your generalized inverse for this problem, damping parameters, etc., and design a checkerboard test. So basically, your synthetic true model will be a checkerboard, which will have these plus this fast and slow anomalies all over the world at some scale, and you want to see how you can retrieve. So in this particular test, there are two tests here. The checkerboard was introduced at a particular depth. So the theoretical model is just a checkerboard at in some depth range, and no model anywhere else. And this is what you retrieve by getting it through the resolution matrix. So what you see is that in this particular example, there is not much leakage into other blocks. You can see that there is a little bit of leakage to the sort of the layer above, but not much below. But you can see that you don't retrieve the amplitude of the blocks equally well everywhere, right? In the southern hemisphere, you have some problems here, which is a well-known problem because we have fewer stations, we have fewer paths that go through the southern hemisphere just because it's covered by oceans, and we don't just even because we don't have enough stations. This is similar checkerboard test, but now down near the Core-Manto boundary. In this particular model, I guess you can see that again the northern hemisphere is better resolved than the southern hemisphere. You can get the shape of these, you recover the shape of these anomalies, the plus minus quite okay, but not the amplitude, right? So this is now, so here you see that the regularization process will degrade in particular, the amplitude of the lateral variations that you retrieve. And this is a point that I want to drive in particular to the mineral physicist, is that when you have a model that you want to interpret, you have to be a little careful at taking at face values the values of the velocities. In fact, the shapes in general, the shapes of the perturbations are much better recovered than the amplitudes. I'll show some examples later. The other thing is that, again, this resolution, people complain about checkerboard tests for various reasons. One of the main reasons is that you have some strong assumptions in this test. First of all, this resolution matrix depends on your G matrix, and remember the G matrix depended on your parameterization, on your theory. Okay, so the theoretical assumptions on wave propagations are in there, and most importantly, it assumes that the problem is linear. You cannot define this resolution matrix in any rigorous fashion if it is a nonlinear problem, because you really have already the assumption of your reference model, your starting model in there. So that's why these tests are quite limited. And if you wanted to do them right, you would want to do them at different scales, different sizes of checkerboards and etc. But it's simpler than doing a spike test, because if you want to do a spike test, you have to do it many times for each block, and takes forever. So,
how would the checkerboard test as you tune that epsilon parameter, say in the damped square?
So, in the checkerboard. So as you increase the damping, you would get a more and more smearing, I guess, and also reduce the amplitude of what you recover.
And if you try and take really little damping, the amplitude will go up, but will something else funny happen? Or? Yeah,
right. Actually, I'm wondering myself what happens, whether you can really tell from this, if you decrease the damping at some point, the whole thing is going to be blowing up. So
no, it doesn't.
No,
not with this inversion.
No, it doesn't.
No, you get
which inversion you mean? Back. You mean this particular example?
Yeah.
Mm-hmm.
For the regions that are well resolved, how well do you get the amplitudes?
Well, that's you get them, by comparison with the original checkerboard. You can see. I mean, it's not given here, but they're reasonably well resolved here. Yes.
I mean.
But again, with respect to the theoretical assumptions that you made.
The magnitudes of your anomalies, that really depends on a data set. But it is possible, even with this type of regularization, if you have a good data coverage and also azimuthal data coverage, you get the amplitudes back with reasonable smoothing to maybe 10%, within 10%, maybe within 20%, if the data coverage is not that optimal. But it is possible to get them within 10%, even with smoothing in post.
Adam?
My comment is, probably it's important to remember that the result of the test will depend very much on your parameterization.
Yeah.
So, for example, if you tested a resolution of degree 2, you might actually get a perfect answer. However, if you want to represent the model by superposition of different harmonics, then obviously, the long wavelength part will be better resolved, and this is why it's very difficult to estimate errors.
But that's why you, as Barbara said, that's exactly why you do checkerboard tests or these resolution tests for different wavelengths. It's exactly what you said. It might actually be that the data set is good enough to constrain a long wavelength structure. And so you will see that a larger checkerboard is actually much better retrieved with this type of inversion than the shorter wavelengths.
Well, it depends, because you can think about these things in wave number space or in space
Geometric.
and dimensional.
Geographical.
And there are advantages and disadvantages. If you want to know velocity anomaly in some particular place, you probably have to go to this type of parameterization. On the other hand, if you want to observe properties of a system that's very much wavelength dependent, then working in wave number space may be more appropriate.
Yes.
Another comment on the resolution, that if you're just to point out that you are assuming exactly the same theory that you used in constructing the model. So if you used a more accurate theory to generate some synthetic data and then inverted that, you might see that you weren't recovering so close to the resolution.
Yeah.
So your Earth model is obviously calculated using your Earth obviously is an exact forward theory compared to what we're using. So your model perturbations could still be a lot smaller than the true values in the Earth.
Yeah, right. So that's an important point. I've tried to make it, but I would like to drive it in, that the resolution is very closely tied to what theory you are computing things in. And for some applications, your theory is perfectly all right, but for some others, it may not be. Yes? These are two different tests. The input model here is a full checkerboard, right? If you had the same kind of amplitude as you have here all over the Earth, in this particular depth, around the depths of, I guess it's 890 kilometers, right? And you push it through your inverse problem as if you were inverting, if it was real. Yes, it's the recovered. Yes. The synthetic is not shown. That's the problem. I'm sorry, but it would imagine a checkerboard, a full checkerboard. Okay, I should have shown it, but I didn't. Yes, all blue and red. Okay, and this is for different depths, right? And you could have a checkerboard test where you would have checkerboards all at all depths, also sort of alternating in depths, red and blue, and whether you recover them. But
well, it essentially shows that you have reasonably good radio resolution, because these checkerboards don't show up adjacent maps.
That's right. Yes.
But at 730, that's artificial intensity that you recovered.
Where?
On the left, at 730.
Yes. So this is what is basically smeared, right? It gives you as Adam said, it gives you an idea of how good your resolution is in depth, because your original model is concentrated in that depth, but you recover some bogus structure at other depths. Okay. I don't know. I mean, let's move on. Okay, so ingredients of an inversion in the context of global tomography. I will not overemphasize, I don't want to underemphasize the importance of sampling and coverage, because as you understand, the most important thing is that if you are in blocks, if you think in terms of blocks, again, this is just an example, then you can resolve the structure in the block if you have ray paths coming from all directions in that block, because that allows you to separate this block from the other blocks, right? So this is sort of the main principle. And so what we're striving for in seismic tomography is to have the best possible coverage. Okay. And as I will show you, this is achieved by mixing different data types. Different data types have sensitivity to different depth ranges, different parts of the world, etc. And so you want to use as many as possible to achieve the best possible resolution. Parameterization we discussed. There are two types of parameterization. I only discussed the geometry, right? Whether you're using blocks or voxels or spherical harmonics or splines of some kind, whether you use local versus global functions. Spherical harmonics are global, right? They describe a function globally with coefficients. The splines, spherical splines, would be a local parameterization. Blocks would be a local parameterization. But we also have the physical parameterization, which is also very important. You know, how do you describe your physical model? What are you inverting for? So the seismic waves are sensitive to the elastic parameters. There is anisotropy, that is the velocity. It depends on the direction of propagation. In many parts of the Earth, that is true, certainly in the upper mantle and also in the double prime. I'll be talking about this a little more next week. And also there is intrinsic attenuation and elasticity. And all of these influence your waves. And so you have to choose an appropriate physical parameterization. And in fact, depending on what you're working with, so if you're working with P travel times are very convenient because they are sensitive only to VP. So you don't have to worry about all these other parameters. But once you get into surface waves, for example, surface waves are primarily sensitive to VS, but they also have a little bit of sensitivity to VP and to density for the Rayleigh waves. And so you have to also make some assumptions. They're not sensitive enough that you can recover these, but you have to make some assumptions on their. In general, for example, we assume that the VP structure is proportional to VS with some proportionality coefficient. The variations in VP, the lateral variations in VP are in the upper mantle. This is a reasonably valid assumption. And same for rho, the lateral variations in density will be proportional to the lateral variations in shear velocity, and you only invert for shear velocity. But you have this hidden assumption there that this proportionality is valid. So parameterization is very important, and if we really wanted to do things right, you would have the full, you would have to describe the Earth in a full anisotropic tensor, and that makes, at every point on the Earth you would have to have 21 parameters of the anisotropic tensor plus density plus attenuation, and this becomes much too much to handle. So we have to make assumptions there. And finally, the theory of wave propagation. And there, for example, for travel times, do we use ray theory, like I was giving you this example, where the travel time is only dependent on the infinitesimal on the structure along the infinitesimal path, or whether we use a broadband theory where we take into account that the wave that we're measuring has a finite frequency, and in which case it will not only be sensitive to the ray path, the infinitesimal ray side, but it will have some sensitivity outside of the ray path. So these are theoretical assumptions. Okay, so let's move on to some considerations about what goes into global tomography. So the simplest is to use first arriving travel times. So P waves arrive first on the seismogram, and so they're the most convenient because there is the background noise in front is if you have good data, is quite low, so you can measure the travel time of the P wave quite precisely, right? Unlike waves that arrive later, which arrive in the coda, the signal generated noise from the P wave, for example, S wave here, in this part of the seismogram, you have lots of other waves that have been bouncing back and forth in the mantle. So the signal to noise ratio when you measure the travel time here is always somewhat degraded. So it's harder to measure the arrival time of S waves. It's harder even to measure the arrival times of any other phase that's after the P wave. Here you will have PP, so the phase that bounces once on the surface of the Earth, etc. All these phases are still these type of phases, PPP, S, and SS, are relatively well measured. So the arrivals are well separated on the seismogram. There are some issues of noise, but they're suitable for travel time measurements. And so, and the other thing is that ray theory for P waves, at least, works pretty well. That is, this basic assumption that the sensitivity is restricted to the ray path, right? So the structure along the ray path is a pretty good first-order approximation. There has been a lot of work done recently on these banana donut kernels, which improve this, provide improvements to this ray theory. But to first order, this is pretty good. Generally, people parameterize in blocks, but not necessarily. But that's sort of the first, the first thing you want to look at are these travel times of body waves traveling through the mantle. And so we've seen many pictures of slabs. I mean, these are some old, relatively old models here by Van der Hilst, and some pictures of plumes, quote unquote. I will argue, and I'll show you why in a minute, that I would believe this picture more than this one, and I'll explain to you why. Simply because of coverage. So we are limited by the coverage, by the events that we can use, right? They're all more or less at plate boundaries, so there are large areas of the world where we don't have sources. And the stations, we also are limited, and in particular, there are fewer stations in the southern hemisphere because we have a few islands, but the rest would have to be covered by ocean bottom stations, which is still a challenge. Right now, it's mainly a challenge of cost rather than technological challenge, but it's still a challenge. So, how do you assess sampling? Well, one of the way of assessing that is to plot ray density maps. So, in each block, which I think is about 2 degrees by 2 degrees, you can count how many rays go through your block. Okay, for P travel times. And while this slide is already 15 years old, it still it still shows the main point. So this is shown at 2 different depths. One just below the 660 kilometer discontinuity, and one at the bottom of the mantle. And you can see here that because of the simple geometry, the limitations of the geometry of the sources of the receivers, the regions which are the best sampled are the regions near subduction zones, right? And near continents and subduction zones. So here in the Western Pacific, and this line in the Americas. By contrast, the middle of the oceans, especially the middle of the Pacific Ocean, is very poorly covered. This is only with P travel times. If you add PP, you will get somewhat better coverage, but it's still a big issue. At the base of the mantle, it's uniformly poor, essentially. Another way of looking at this is, of course, checkerboard again. And what's here shown is the results, the output of the checkerboard. Again, it's the input checkerboard is all over. It's the same pattern throughout the globe. And this is showing only the output. And it's shown at different. This is work from Carson and Van der Sis also a while ago, but showing at 1,000 kilometers depth, 1,500, 2,000 kilometers, and near the CMB. And you can see that you recover your checkerboard quite well in the same regions which were sampled, which showed good ray density in the previous slide in all these depth range. As you get into near the core mantle boundary, you see that there have been assumptions made here that you can recover only larger scale. So the blocks that have been put in this resolution test are larger size because of this limited coverage. And what's shown here is a comparison of what you get if you include only P waves in your inversion, or if you include P and P diffracted and a core phase PKP at the time of this work. This is the improvement. So you do improve by including these diffracted waves. you improve the coverage and therefore the resolution in the southern hemisphere. We had some discussion about this a couple of days ago. So on the other hand, near subduction zones, you have a lot of earthquakes, you have a lot of stations, and so you can also include paths that are, that are not necessarily only teleseismic paths, and so you can get a very good geometry of many rays crossing and also coming from many different directions into a particular model parameter. And so this is just an illustration of a recent model by the Fukao group of cross sections across Honshu and northern Bonin. So these are the Honshu sections, these are the northern Bonin, which show the subduction, what happens to the subducted slab in this region, which seem to indicate, as Adam stressed on Tuesday, that there doesn't seem to be much going on below 660. This is 660. This is 1,000 kilometers. In contrast, if you look at a cross section, yes.
So the fading of the slab subducting through the transition zone in the Vanderhills paper, is that a result of the way the lower mantle is parameterized in those models, or is there a physical basis to that?
Well, you mean the picture that I showed earlier?
So it gets larger or gets wider as it goes deeper into the mantle?
Well, so these were older models with fewer data, and so most likely much of it is still pretty. This one you were talking about? Is that the one?
There's a general trend for the slabs to get wider.
To get wider, yes. Well, that in itself is also seen in the newer models, right? They get wider. And why they get wider is for the geodynamicist or, mineral physicist to tell us.
It's not an effect of the parameterization?
No.
But it is interesting to compare that E prime in this image, which I think is the same region.
Yes. So yes, exactly right. So it's changed. Yes, that's true. Good question. This is something we struggle with, and I will. I can anticipate. At the end, I was going to mention methodology. There is no real good methodology to estimate the error in these tomographic models. What people do is they do bootstrapping, so that they remove some part of your data set and invert and see what comes out, and you do this many times and you have an estimate of an error, but it's not really very satisfactory. The real way to do it is actually not to do inversion, but to do forward modeling and generate many models, all the models you can possibly generate, and then you can get a full estimate of the errors, etc. So
this conical nature of the anomaly on FF prime could be geometrical, because as the cone of rays goes farther, it widens.
Yeah, I will show you some, more explicit picture of this. So let's see. So this is in Honshu, where you see the slab. I think at this point I would say this is pretty well resolved. It agrees with the tomographic models that I will be discussing a little bit later, which are based on including many more types of data than just travel times. And then as Adam showed on Tuesday, this is in Tonga Kermadec, where it seems that the slab is actually penetrating below the 660 kilometer and ponding at some deeper depth. This is sort of the main kind of focus of this paper, which actually is not published yet. But and this is the region where, in the global models that Adam was showing, this is one of the regions where there is also some anomaly below the 660 kilometer discontinuity. So there's good agreement. Now about the smearing. Yes.
The resolution of these models change with depth. So issue whether the reason we don't see the blue in the lower mantle is because we couldn't see it even if it was
In order to address this question, I would have to show you array geometry, which which was not provided with these slides. I expect that you look at those sampling maps, right? Or this one here, 1,000 kilometers, 1,500 kilometers. In this region, you have relatively good sampling. Now, of course, this is not the same study or whatever, so you have to, but it looks okay near the subduction zone. So now this is showing some of the problems with having only travel times. So what's compared here is cross-section. This is the cross-section across the Pacific. And these two different models. S40 RTS is the recent Ritsema model, which Adam discussed, which contains many different types of data. And at the bottom is a comparison with the Princeton 2005 model, the S model, for exactly the same cross-sections. Here you have the Fukao and Kobayashi model, which includes regional data. And what you can see two things, two problems with this model. First of all, you can see this, for example, this thing here. This is a streak which is not present in this model, and you might say, well, maybe that's because this model isn't resolved. But what's suspicious about it is that here this is exactly where Easter Island is. This is the station here, Easter Island. And there are no other stations around, so you can imagine that there are no rays that can cross here and resolve the structure. So this streak is very suspicious and sort of manifests the inadequate sampling. There are other problems here. You can see this streak here. This is only teleseismic. You can see this streak here going off. I mean, in this direction, the subduction zone might look okay, but this is pretty clear to me, at least, that this is because there was some either station or some pass here that didn't have much crossing rays going through it. The other thing that you can see in this slide is that the top of the model, right? There's nothing on the top of the model here. There isn't. This model, which includes surface waves, has much more structure. It shows the strong low velocity in the East Pacific rise, and then the thickening of the lithosphere towards the subduction zones, for example. And it's on the other hand, it doesn't resolve the subduction zone very well because it is a long wavelength model. It only resolves long wavelengths. But anyway, this was just to illustrate that if you only use travel times in a global tomography, you will never resolve the uppermost mantle, and you will have problems in the oceans because of the inadequate sampling. Now, this model was derived using finite frequency theory, right? So even with finite frequency theory, you have the same problems, just because even if your ray path is, if you have more sensitivity outside of the ray path, you just don't have enough to cover all of the space.
Ignoring the latter point that the surface is not adequately covered, just for our own intuition, if I did a tomographic inversion and I got this image on the bottom and I saw that streaking, what do you do to fix it? Because I guess if you're a careful seismologist, first thing you'll say, Easter Island, that's like one station. And
well, you add other data.
So, I mean, would it be? If you didn't add other data, you would. I
just wouldn't show it.
Would you dance wrong? Or.
So in that paper, they don't explicitly say in the paper how they did the damping. But if you talk to some of the authors in private, what actually happened with that model is that they wanted to image the plumes, and so they forced a very strong radial smoothing, so smoothing with depth. They imposed a very strong vertical smoothing in their inversion on a data set. And you typically would not do this.
In other words, smearing.
a lot of smearing, that causes a lot of smearing, yes, because they wanted to see small scale structures in the mantle going down.
Okay. So the bottom line is, you can't just do it with telescopes unless we cover the oceans completely with stations, etc., which would be great. But okay.
I'm wondering why in the upper left panel it's so smooth in the depth image 1,000 kilometers. I mean, in the Adam's lecture yesterday, 2 days ago, there's some variation in the lower mantle, right?
Oh, it's big. It's a color scale. You know, first of all, I don't. You know, there is. If you look at it, there is a little bit of blue and red, etc. It's just that the strength of the anomaly just becomes very, very low in the lower mantle. So depending what color scale you use, you know, it's.
But there's no inspiration why the left should go horizontal around 1,000.
That's you know something to think about. You know why that would be.
Comment on that just briefly, and maybe in the discussion section, our geodynamicist colleagues can comment on it. I get heckled a lot when I use words like pondine or slab is held up by the 660, and the guy down the hall tells me, no, you can't say that. Really, if it is a viscosity increase, it's just slowing down. You could think of it as time. It's not stopping. So if it slows down, it becomes more horizontal. And so, yeah, I think, well, that's ponding, right? But I get heckled about the use of terms there because it's just delayed on its way down.
But there's
Max?
also density crossover in exergite, so the sucking step will bring a lot of exergite into that. So if it crosses that 660 boundary, exergite will turn buoyant before it was negatively buoyant.
I thought, is that new result for that? Hirose said it gets sensitive.
No, Hirose says it gets actually positively buoyant between, I mean, you might know more about it, between about 700 and 800 kilometers.
Well, I plan to cover some of this slab morphology in my lecture, and people can have me when I use ponding.
But you can see that in the long wavelengths model, this structure, the blue structure here is present. It's not. It's the same as this one, around just below, around 670 kilometers. It's there.
But stagnation is well, I don't know, maybe
a better word.
Invent another word, but essentially, there's flattening. In the particular case of that profile there at the top, it's very puzzling because there doesn't seem to be any global change at that depth. So, but
in the spectrum, you mean?
In the spectrum. Well, this picture is very impressive, and it part of it may be that there is also Vanuatu. There are essentially two subduction zones merge, and it is pretty complicated.
Yeah, and this is sort of grazing, these subduction zone areas. So anyway, so the bottom line is, if you want to get better pictures, you have to have many types of data. So surface waves, we saw, we discussed surface waves. I wanted to, and Adam also discussed overtones, but I just wanted to kind of clarify a little bit. So in surface waves, you have the fundamental modes, which here, so this is an observed and this is a synthetic seismogram. Just look at the observed, for example. So this is the R1 train, and then this is the R2 train, which are relatively well separated on the seismogram. So you can kind of analyze them separately. This would be the fundamental mode. But in front of it, you have this bunch of energy, which is basically these combinations of body waves which are coupled together to form these overtones, these higher mode surface waves. Okay, and the interest of the higher mode surface waves is that their sensitivity with depth depends on which mode you're looking at, and they reach deeper into the mantle. So the comparison here is a fundamental mode Rayleigh wave at 40 seconds is sensitive, the green one sensitive primarily around 30 kilometers depth. At 100 seconds, it's say about 100 kilometers, roughly speaking. Then if you go to longer periods, you start sampling the deeper mantle, but you see that at 200 seconds, you're still mostly sensitive to the upper 200-300 kilometers. Whereas if you add overtones, you see that at the same period, say here at 150 seconds, let's compare the blue lines, this first higher mode has some sensitivity here in the transition zone, or even deeper, right, compared to the fundamental mode, and if the second higher mode, even more so, etc. Right? So by adding overtones, you add sensitivity from the top. Now looking from the top, where surface waves give you the sensitivity to the top 200 kilometers, if you add overtones, you increase your sensitivity to deeper parts of the upper mantle and transition zone. So Adam showed this slide already on Tuesday. This is one made by Ritsema, where he compares how the model looks if you include only fundamental mode surface waves. Then you basically lose resolution, certainly in the transition zone, and you don't recover anything deep in the mantle. If you add overtones, or if you have overtones only, you pretty much can resolve down to bottom of transition zone, but not in the lower mantle. And the body waves really start giving you are necessary to resolve the structure at the bottom of the mantle, but by themselves they really don't recover. You can't do an upper mantle model with body waves. Now I realize you may be confused because I just showed you these cross-section by Foucault, but these cross-section by Foucault are regional, they use regional data. So this is really only using this teleseismic data, this data for waves that travel long distances and therefore they start very steeply from the earthquake source. An important component at the base of the mantle are diffracted waves and multiple SCS waves. I put the slide up because there was some questions about this. So in addition to the direct body waves, direct S waves, say, you can include diffracted waves, waves that diffract along the core mantle boundary, so they're very sensitive. These are broadband sensitivity kernels of the S diffracted, which is concentrated along the core mantle boundary, and multiple SCS. This is shown SCS2. Again, it samples the whole mantle, but it allows you to get some sampling in the deep mantle, even for large distances between the source and the station. Yes.
Do the shadings have a meaning?
Yes, these are sensitivity kernels. And I'm trying to think. I think the white means large sensitivity. White means positive, and dark means negative sensitivity, and the gray means zero sensitivity. It's not a very good picture. I'm sorry. It's what I grabbed yesterday. But okay, so this is another slide borrowed from Guy Masters, comparing the sampling in the deep mantle that you can get with only S waves, right? The direct S waves. Only P waves, and then if you add diffracted waves, you see that you start filling in some of the gaps in sampling, and same for the P models. Okay, so now, so we've discussed the advantages and disadvantages of travel times, the fact that you can add surface waves to constrain the top of the models, the top of the mantle. Overtones give you some sensitivity to the transition zone. But in a seismogram, there's much more information than that. There are all these phases that bounce around everywhere. they're not very well separated. This is a travel time curve identifying many of these different phases that sample the mantle. And you would really want to use all of this information because that's going to help you illuminate the whole mantle. And really to do this, because most of these phases cannot be separated on the seismogram. You can separate P, you can separate S, you can separate SS, you can separate the fundamental mode surface wave, but in between it's very hard to separate these phases. So really you have to work with waveform, with the full waveform. So that's where the field is going today, nowadays. So we're so, for example, so this is work we've been doing at Berkeley for a long time. Actually, what you do is you compare a seismogram in the time domain, or you could do it in the frequency domain, but a whole seismogram to a synthetic. So you have to have a way to compute the synthetic. So the theory starts to matter there, how you compute this theoretical seismogram. And then you can also you window your seismogram so that you can isolate arrivals of energy, because if you don't do that, then the waves that dominate the seismogram will dominate in the inversion, and these will always be the surface waves at long periods. So you set up an inverse problem, which is comparing your point by point, say, for example, your synthetics to your observed in some wave packets, and that's what you invert. The difference is that now you compute a complete seismogram instead of computing travel times of either body waves or surface waves, right? When you measure phase velocities, you are actually measuring travel times of surface waves, which depend on frequency. And so for surface waves, array theory, which assumes that the sensitivity of the surface wave is along the ray path also, so is limited to the great circle path between the source and the receiver, and only to the average structure, is a good approximation. But for the overtones and for the body waves, that's not a good approximation, and this is shown in this slide where we compare sensitivity kernels for what is called the path average approximation, or it's sort of ray theoretical approximation. So path average approximation assumes that all your waves are sensitive to is just a 1D model, right? Only varies with depth along between the source and the receiver. This is clearly not a good approximation for rays, for body waves like SS, right? Because they're mostly sensitive to the ray path, not just the average structure. And so these are example for SS. This is example for S diffracted. However, there are ways now to include these sort of finite frequency effects that allow you to represent the sensitivity much better. For example, for this body wave, again, the dark here means a lot of sensitivity in the positive sense, white in the negative sense, and then gray, there's no sensitivity. So the introduction of this improved theory makes it possible to actually use body waves in a waveform context. And this is just an example of a checkerboard test, just showing that if you invert with the path average theory, which is this 1D kernel theory, you do a pretty good job at the top of the mantle. Again, the input checkerboard is just black and white, strong black and white. You do a pretty good job at the top of the mantle because the surface waves are very well approximated by the theory. But once you get into the lower mantle where the body waves are important, then in the context of waveform tomography, you lose resolution. Whereas if you include these kind of more accurate theoretical kernels, you can resolve structure better at the bottom. So, nevertheless, this is a comparison of 4 models that I think Adam showed, recent models at depth of 2,800 kilometers. This is just to show you. So these models have been determined with including a lot of travel times, surface waves, for some of them overtones, mode splitting coefficients, etc. This model was obtained only using waveforms at periods greater than 32 seconds, but many of these wave packets. One can argue forever whether this model is better than the others or whatever, but the point is it gives you a structure which is very compatible with the other models, but now based only on the waveforms. So we have a tool to do this. The point I want to make here is that, again, remember that because you have damping in your inversion, no matter what, you lose the ability to really determine the accurate value of your lateral variations in velocity. If you compare these maps, in the large scale, they show very good agreement in the shapes of these superplumes, as Adam showed on Tuesday. However, if you look in detail, the amplitudes, there are large variations in amplitude in these models. And in fact, it can be shown that the amplitudes are underestimated in these models at this scale. So, for example, here this is a sort of an exercise where we looked at ray paths from Fiji to an array in South Africa, looking at diffracted waves on the core-mantle boundary. This yellow indicates the path of the diffracted waves on near the core-mantle boundary. And we're sort of going through into the African superplume, which is red here. This is one of the background models. It's one of our Berkeley models. And the blue is outside of the superplume, and you're going into the superplume. And what you see when you look at these data in detail, you see a lot of complexity. This is as a function of azimuth. So starting at smaller azimuths, you're going into the superplume. And you see a couple of effects. You see that the S wave is very much delayed inside the superplume. It's about 10, 15 seconds. And you see this complexity here in this region. You have these secondary arrivals that you don't have outside of the superplume. These are different frequency bands. And there's no way you can explain this with existing tomographic models. So this is some synthetics done in a numerical model. This is the original. This is a different projection, but again, we're looking at here. There's the fast, and here is inside the superplume, and this is what's predicted in the tomographic model as it is. But if you keep the boundaries of the model as they were and simply saturate the model, make the amplitudes larger, here plus or minus 4%, you can start seeing these large effects of travel time delays and these secondary phases arriving. So this is just to illustrate that the amplitudes of lateral variations in the tomographic models, certainly in the deep mantle, are not quite accurately determined of the problem of damping in the inversion. Okay, so now moving forward, I think this ability to do waveform tomography has recently been really got a boost from the moment where the synthetics could be accurately computed using numerical methods such as the spectral element method. Previously, those synthetics that we used for our models were based on normal-mode perturbation theory, which makes a lot of assumptions about the smoothness of the lateral heterogeneity. You have to have smooth heterogeneity for it to work. With the numerical methods, all of these assumptions on what kind of heterogeneity you are computing your synthetics through is removed, so you can compute very accurate synthetics. And this is work in progress that several groups in the world are working on right now, both at the global scale and at the regional scale, but which shows some promise. And so I'd like to, in the final minutes, I'd like to illustrate why I think this holds promise. So in this picture, I compare a model that we obtained recently using these numerical synthetics for the upper mantle to this model by Ritzema. It's not the latest one, but the differences are not that important. And you can see that if you look at these two maps, these two series of maps, they look very similar. So basically, this means that 30 years of tomography was not, doing approximate theories is still gives you some reliable information on the mantle. But if the important difference is really in the amplitudes of the perturbations at the top. You can see that here the peak-to-peak amplitude of the lateral variations are plus or minus 10, it's minus 12% to 8%, whereas in the previous model it's only minus 7 to 6, and this difference somewhat persists deeper, but it's primarily visible at the top of the model. And I believe this is actually, it's a reliable result, and it simply means that the equations are more consistent because you're using a more exact theory, so you can recover the amplitudes a little better. This is a cross-section across Africa, one like this, east-west, and one north-south, again illustrating the very strong lateral variations here that we are recovering in these models. Here in this one particularly, it's peak-to-peak almost 20% at 100 kilometers depth. You see the craton very, very clearly, and this would be the getting into the Red Sea region. Another example here, again, I'm insisting on the potential of this because these are sort of preliminary, very first results using these methods. Here, we're comparing a depth profile of shear velocity in the East Pacific Rise in a location where there are actually local data. So the model obtained with the local data is this model by Harman, which is here, compared to the velocity profile from two different global models, recent global models. And you can see that the global models do not reach these low velocity anomalies that can be reached at the local scale with local data. This is, for comparison, a profile in the Western Pacific showing that the low velocity minimum has become much deeper. The model, Ritsuma's model, has this jump because they include the 200-kilometer discontinuity, so it looks a little funny because of that. And then if we compare with the model we are obtaining now with the numerical models, this is the green line here. You can see that we're starting to match the minimum of the low velocity where it should be. And so this is quite encouraging because, of course, we don't have, these local deployments are available only in very specific places in the oceans, and so there is perhaps hope that with global tomography we can actually reach better resolution, not only of the shapes but also of the amplitudes of low velocity anomalies. And low velocities are particularly important because the theory becomes very important because of this what's called the wavefront healing effect, is that when you have a wave propagating through a slow anomaly, the waves will have a tendency to go around it because the faster waves around it will travel faster, so they will sort of obliterate the effect of the low velocity anomaly. So these become very subtle effects for which you need a better theory too. And so this is again preliminary. This is the same cross-section. This is STRTS. This is the working model that we have right now in the same region. And you can see there's a lot of similarities. In the large scale, we see flow velocities where they see slow velocities, etc. But in details, there's stronger low velocity anomalies, and somewhat we start to separate perhaps what are conduits through the upper mantle. But again, I don't want to spend too much time. You can see the subduction zones start to be a bit better resolved. And if you compare this one with this one, you can see this trend of I don't want to say ponding, but what was the word in the transition zone and a little bit below. Okay, so in summary, what's important in global mantle tomography? Sampling is absolutely critical. It's really the first thing you have to worry about. It's improved by inclusion of different types of data: surface waves, overtones, body waves, diffracted waves, whatever you can include. Now with waveforms, we can start including everything. The theory to constrain better amplitudes of lateral variations as well as smaller scale features, there is potential in improvement of this in the future. Physical parameterization I did not talk about at all. I will talk about it a little bit on Thursday next week, or whenever is my talk next week. In particular, the effects of anisotropy are very important. And we already discussed that parameterization is something that is also kind of tricky. I did not discuss error estimates. There was just one question about it. I suggest that at the presentation that Thomas Baudin made last week, during the first week of CIDER, it's up on the web, which illustrates some of the new methodologies which allow you to do forward modeling, to get rid of the inverse part, and so you forward model many models, and there are ways to do this efficiently, and also to then that provides a way to, in particular, to provide errors on all the parameters, the trade-offs between different parameters, etc. So I should stop here. Somebody asks me about the 1D model. I will be happy to answer, to show one more slide, but I think I should stop. Thank you.
In addition to structure that is resolved, it's of interest to know the statistical properties of unresolved structure. Yes. What can be said about that? That is to say, variations which are on length scales large compared to the wavelength, but smaller than your resolution. It would be even interesting to know the simplest possible things, like whether there's more of that in one large region of the Earth compared to another at great depth. Is it possible to say anything about that sort of thing?
So there are studies that try to look at the statistical properties of seismograms and phases, etc. One I can think of is a study of precursors to PKP.
Yes, I know about
right?
precursors.
So
it seems kind of specialized in terms of the range that you can look at.
But you can also look, for example, at the coda of the P wave, which tells you about all the bouncing waves beyond the main P waves. So that will tell you more about the. You can treat that statistically and say something about the length scale of structures in the crust or uppermost mantle. I don't have much of a. Yes, Vernon. Vernon is a specialist. That's right, of statistical stuff.
Major gap, though, in knowing what the heterospectrum is between where tomography can resolve it, where photo waves can start to predict it. So there are big gaps in the knowledge of the heterospectrum.
But probably could be addressed somehow, especially if you have possibility of resolving directions of approach of scattered waves. What would be provided, for example, by this global array of arrays.
The reason why it's important, of course, is that thermal anomalies can diffuse away, whereas compositional anomalies cannot. And so this is a way of addressing the question of whether your anomalies are thermal or compositional.
So, I can think of many studies that have addressed something in a very particular region, say through, again, looking at at precursors or postcursors of such and such a phase that will tell you something about the scale length of some heterogeneity in some particular region. But there is no, as Vernon says, there's
certainly 1 to 10 kilometer heterogeneity, which upwards to 50 kilometers, similarly in the whole time, and those are only to be explained by chemical heterogeneity, not by thermal.
You see those things down into the mantle as well in subduction zone vicinities. Down to 1,000 kilometers.
Yes, or even more, yes.
Yeah,
Sure.
more.
Do you have a question?
A different question. You showed this map with the ray coverage, how many rays hit a certain area. And I was thinking, would it make sense, or maybe people do that, I don't know, to adjust the size of your blocks locally to how many rays
Yes,
are hit?
they do that. Yes, that is done. Yes, absolutely.
In your talk, you showed some check-your-ball tests to the resolution of the inversion matrix. But I'm wondering whether people do some tests, whether a method is applicable to the scale of the rupture of the velocity anomaly. Because generally there are 2 ways to do tomography, using the ray theory or the finite frequency. And basically it's based on 2 different assumptions. Finite frequency is based on one, the anomaly is really small comparing to the wavelength. So intrinsically, ray theory is sensitive to the really large scale anomaly. And
That's true. Yes, that's absolutely
and the
true.
finite frequency is sensitive to the really small scale.
Yeah.
But it seems to me, if people know some theory...
Well, you're talking in the context of travel times.
Yes.
Right. Because if you use waveforms, it's true. If you use just Born, the finite frequency Born approximation, the banana donuts, they are assuming small-scale heterogeneities. You will not recover the long wavelength heterogeneity this way. So you have to combine, really. Okay, I don't know, so nobody's moderating? Oh, I see, okay.
Negative 7 minutes left.
Okay, well, I think we should break up for the coffee.